Good morning, students. Today is the science session on electrochemistry. In today's session, I'll be discussing about potentiometric titrations. So, under potentiometric titrations in the syllabus, it is mentioned about acid-base titrations, redox titrations, precipitation titrations, and complexometric titrations. So, out of these four different types of potentiometric titrations, in this session, I will be discussing about acid-base titrations and redox titration. So, one of the applications of EMF measurements is in the field of potentiometric titrations. So, you are all familiar with routine titrations involving usage of indicator. You might have in your PS2 as well, in your PUC as well as first year degree course, you have carried out normal titrations, maybe acid base or redox titrations using an indicator, and you calculated amount of the given substance by performing normal titrations by observing change in color of the solution. So during normal titration, the presence of indicator, you add the titrant till there is a permanent color change in the solution. Then once you observe color change in the solution, you stop the addition of titrant, and noting down the volume of titrant, you calculate the amount of a given substance in a given solution. So that's normal titration. And we can also perform these titrations by instrumental methods. So titrometric analysis is one of the methods of quantitative analysis. So this titrometric analysis can also be carried out by instrumental methods like potentiometric method. Other instrumental methods are conductometric method, spectrophotometric method, amperometric method, etc. So what are these instrumental methods of titrations? In potentiometric titration, we determine EMF of the solution for different volumes of titrant added. So it is a potentiometric method. In conductometric method of titration, we measure conductivity of the solution for different volumes of titrant added. In spectrophotometric titration, we measure absorbance of the solution for different volumes of titrant added. In amperometric titrations, we measure amount of current passing through the solution for different volumes of titrant added. Right. So, in all these instrumental methods, we study one of the properties of the solution, then plot a graph of volume of titrant versus that property studied. For example, in potentiometric method, we determine EMF of the solution for different volumes of titrant added. For example, I add 0.1 ml of titrant each time, and I determine EMF for each 0.1 ml of titrant added. And then I plot a graph of volume of titrant versus EMF. And from the graph, we determine equivalence point. In a routine titrations method, where you observe color change, there you determine endpoint. But in instrumental methods of titrometric analysis, you determine equivalence point. Endpoint comes immediately after equivalence point. Equivalence point is that point during the titration where equivalent amounts of a titrant and titrand are added. So that is equivalence point. Equivalence point is the point at which equivalent amounts of two reactants are added. And endpoint comes after that. So in all instrumental methods of analysis, we determine equivalence point from the graph of volume of titrant versus the property that is determined. In conductometric method, we plot graph of volume of titrant versus conductance. In spectrophotometric methods, we plot a graph of volume of titrant versus absorbance or optical density. And in amperometric titrations, we plot a graph of volume of titrant versus current. And in potentiometric titrations, we plot a graph of volume of titrant versus EMF. So from these graphs, it is possible to determine the volume of titrant consumed by known volume of titrant taken in the titration vessel. So this is the principle in the instrumental methods of titrometric analysis. The equivalence point is determined from the graph of volume of titrant versus the property that is studied, right? So in potentiometric titrations, I repeat, what is the principle underlying potentiometric titrations? The principle is that with the addition of aliquots of titrant, there is a change in EMF. And as the EMF changes, a graph of volume of titrant and EMF can be plotted, from which we can determine the equivalence point, right? So, by potentiometric method, we can study the 4 categories of reactions: acid-base titrations, redox titrations, precipitation titrations, and complexometric titrations, right? Now let us consider an acid-base titration performed by potentiometric method. Let us now discuss acid-base titration performed by potentiometric method. For example, let us consider the titration of hydrochloric acid solution against sodium hydroxide solution, right? So we take about 20 ml or a particular volume of SS solution in the beaker. Then NaOH is taken in the burette. And as we add NaOH to HCl, what happens? The reaction that takes place here is that sodium chloride is formed. So as we add more and more of NaOH, H plus ion, this is an ionic reaction, H plus Cl minus, because HCl is a strong acid or it's a strong electrolyte, it dissolves completely. And sodium hydroxide is also a strong base, it dissociates completely. So when we add, say, 0.1 ml of NaOH, so H plus ions of HCl are removed as undissociated water by the reaction with OH minus ions. H plus ions of HCl react with OH minus ions of NaOH, resulting in the formation of unionized water. So as we add more and more of NaOH, there will be continuous fall in hydrogen ion concentration. So if we can measure change in EMF due to change in hydrogen ion concentration, then we can perform this titration by potentiometric method. So here, since there is change in hydrogen ion concentration during the titration, we have to choose an indicator electrode whose potential depends upon hydrogen ion concentration. And we already learned while discussing about determination of pH using quinhydrone electrode or glass electrode. So pH is a measure of hydrogen ion concentration. So while discussing there, I said an indicator electrode whose potential depends upon hydrogen ion concentration can be used as an indicator electrode. So what are those electrodes whose potential is sensitive to hydrogen ion concentration? Hydrogen electrode, quinhydrone electrode, and glass electrode. So of these 3 electrodes, we choose any one as an indicator electrode and couple it with the calomel electrode, which is a reference electrode, and determine initial EMF, then determine EMF of the solution for different volumes of titrant added. So as the hydrogen ion concentration changes, EMF of the cell also changes, because calomel electrode potential remains constant. As hydrogen ion concentration changes, electrode potential of indicator electrode changes. So overall EMF changes. So this is the principle. So during potentiometric titration of HCl against NaOH, H plus ion concentration decreases continuously, thereby EMF also changes. And whether EMF increases or decreases during the titration depends upon which indicator electrode is used. Let us see that. So when we use quinhydrone electrode with the calomel electrode, so quinhydrone electrodes, E naught of quinhydrone is 0.6996 volts, whereas E of saturated calomel electrode is 0.2422 volts. So when we combine quinhydrone electrode with calomel electrode, quinhydrone electrode functions as cathode, right? So when we combine this electrode, we can represent this as the cell system made up of quinhydrone electrode and calomel electrode can be represented as so this is the representation of the cell involving calomel electrode and quinhydrone electrode. So HCl solution, about 20 ml of HCl is taken in the beaker, and if 20 ml of HCl is taken in the beaker, a pinch of quinhydrone is added, then a platinum electrode is dipped and calomel electrode is dipped into same solution, then they are connected to potentiometer, right? So by taking known volume of HCl in a beaker and by adding a pinch of quinhydrone to the HCl solution and placing calomel electrode and quinhydrone electrode into the HCl solution and connecting these two electrodes to a potentiometer, we can determine EMF. So before adding any NaOH, determine initial EMF and then add 0.1 ml of NaOH each time, mix well and note down the EMF. Now let us see. So when we are using quinhydrone electrode and performing the titration of HCl against NaOH, what happens to EMF? Does the EMF decrease or increase? So since calomel electrode acts as anode here, so E cell is equal to E quinhydrone minus E calomel. And the quinhydrone electrode potential is given by the expression 0.6996 plus 0.0591 by 2 log of H plus minus E calomel, right? So look now, this is the equation which gives EMF of the cell during the titration of HCl against NaOH using quinhydrone and calomel electrode. So now as we add NaOH, more and more of NaOH, more and more of H plus ions are removed as unionized water. So there is a continuous fall in hydrogen ion concentration. So as hydrogen ion concentration falls, this value decreases. So overall what happens? EMF of the cell decreases. So as long as HCl is present, EMF goes on decreasing. So once all your H plus ions are consumed, then EMF becomes negative. Why? Let's not worry about right now. So during the titration of HCl against NaOH using quinhydrone and calomel electrode system, EMF goes on decreasing and becomes negative. Once it becomes negative, we take 4 to 5 readings and stop the titration and plot a graph of volume of NaOH versus EMF. From the graph, we calculate the volume of sodium hydroxide required to neutralize completely the known volume of HCl taken. Right? This is the principle. Okay. Now let us see. So we have understood the principle that whenever we use quinhydrone calomel electrode systems for titration of HCl against NaOH, EMF goes on decreasing, and after the equivalence point, EMF becomes negative. So we take 4 to 5 EMF values on negative side, stop the titration and plot the graph of volume of NaOH versus EMF. From the graph, we can determine volume of NaOH consumed by the known volume of HCl taken. So that's the principle. Procedure is very simple. Pipette out 20 cm cube of given HCl solution, fill the burette with NaOH solution, place quinhydrone, platinum electrode and calomel electrode into the solution, add a pinch of quinhydrone, connect it to the potentiometer, and start noting down the EMF for different volumes of titrant added, and continue the titration till EMF becomes negative. Once EMF becomes negative, take 4 to 5 readings on negative side and stop the titration. Then plot the graph of volume of titrant versus EMF, volume of NaOH versus EMF. So as we learn, with quinhydrone electrode, calomel electrode system, EMF gradually decreases, and at the equivalence point it rapidly decreases. So we get a graph of this fashion. So wherever the graph cuts x-axis on which volume of NaOH is taken, volume of NaOH corresponding to this point of intersection is volume of NaOH consumed or required to neutralize. Say if 20 cm cube of HCl is taken, this is the volume of NaOH required to neutralize completely 20 ml of HCl taken. So this is how from the graph of EMF versus volume of NaOH we can determine volume of NaOH consumed by the HCl for its complete neutralization. And this from this graph it would be slightly difficult to determine the exact volume of NaOH because we join the points with a smooth curve, and there may be a slight error when we join the last positive value and first negative values. So there may be a slight error in the volume of NaOH determined from this graph. So to overcome the difficulty, another graph is plotted, which is nothing but volume of NaOH divided by delta E over delta V. This is called first differential graph. Delta E over delta V. What is delta E? Change in EMF. For example, we have added 0.1 ml and 0.2 ml if this is E1 and this is E2. So upon adding 0.1 ml of NaOH, what is the change in EMF observed? So I can write it as since EMF is decreasing here, I can write it as E1 minus E2 by delta V is 0.1. So each time we are adding 0.1 ml, so delta V for each value is 0.1. You can determine delta E, that is E2 minus E1 minus E2. So this is called first derivative graph. And when we plot this graph, volume of Na versus over delta E or delta V, we get a graph of this fashion. May not be a smooth curve like this, it can also be sometimes like this. So we get a peak. So volume of NaOH corresponding to this peak would be the amount of NaOH needed for complete neutralization of HCl. So this is how we can perform acid-base titration by potentiometric method using quinhydrone electrode. So using quinhydrone electrode we found that EMF is decreasing continuously and becomes negative at the equivalence point, and thereafter after equivalence point EMF becomes negative. So there is a continuous decrease, and at the equivalence point, around the equivalence point there will be rapid decrease. Suddenly till the equivalence point there is a gradual decrease, around the equivalence point there will be sudden decrease in EMF and becomes negative, right? Now instead of quinhydrone, if we take say hydrogen electrode, because in some textbooks they take hydrogen electrode with calomel, or they take glass electrode combined with calomel electrode. In some books they take the example of quinhydrone electrode coupled with calomel electrode. So if it's quinhydrone electrode coupled with calomel, during the titration of HCl against NaOH, there will be continuous decrease in EMF. Now let us see what would be the change in EMF when we use hydrogen electrode, hydrogen gas electrode plus calomel electrode. And we know E naught of hydrogen is 0. We have learned this. Electrode potential of standard hydrogen electrode is assumed to be 0. Right? So here E naught of hydrogen gas electrode is 0, and E that of saturated calomel electrode is 0.2422 volts. So when we couple calomel electrode with hydrogen electrode, now calomel electrode acts as cathode. In the earlier case, twin hydron and calomel electrode, their calomel electrode acts as anode, twin hydron electrode acted as cathode. Same calomel when combined with hydrogen electrode, calomel electrode now acts as cathode. So E cell would be equal to E calomel minus E hydrogen electrode. Right, and hydrogen gas electrode potential of hydrogen gas electrode is given by E naught, isn't it? E naught of plus 0.0591 log H plus, because the electrode reaction at hydrogen gas electrode is this. We write a 2H plus or 1H plus, equation remains the same. So this is the electrode potential of hydrogen gas electrode, and standard electrode potential of hydrogen gas electrode is 0. Therefore, the electrode potential of hydrogen gas electrode is given by this expression. Right. So here, calomel electrode is acting as cathode. So E cell now would be equal to E calomel minus E hydrogen electrode. E calomel is saturated calomel, 0.2422 volts minus of 0.0591 log H plus. This is E cell. Look, this is the expression for EMF of the cell when we are using calomel electrode with hydrogen gas electrode. Now, as usual, we take say about 20 ml of HCl in the beaker, then place platinum electrode and calomel electrode and pass hydrogen gas at constant pressure to this HCl solution. Then we measure EMF, and NaOH is taken in the beaker. So as NaOH is added, H plus ions of HCl are removed as unionized water. So as more and more of sodium hydroxide is added, more and more of H plus ions are removed from the solution, and therefore there is a continuous fall in hydrogen ion concentration. So as there is a continuous decrease in hydrogen ion concentration, what happens to EMF of the cell? EMF of the cell now increases because this minus. Look at this expression. As H plus ion concentration decreases, net value of this right hand side equation increases. So contrary to the earlier system where we considered twin hydron and calomel electrode system, where EMF was decreasing continuously, here on the other hand EMF is increasing continuously, because now calomel electrode is acting as cathode, and your hydrogen electrode as well as same explanation holds good for glass electrode also. Even when we combine glass electrode with calomel electrode, same calomel electrode acts as cathode, your glass electrode acts as anode. So what I want to say is that whenever we use glass electrode, calomel electrode cell, or hydrogen gas electrode, calomel electrode cell for acid-base titration like HCl against NaOH, so in this case EMF goes on increasing. Till the equivalence point, EMF gradually increases. At the equivalence point, there is a sudden increase. So once you observe a sudden increase in the EMF, after sudden increase, take to 4-5 readings of EMF, then stop. Then plot a graph of volume of NaOH versus EMF. Right? So here, we have seen what would be the nature of the graph for volume of NaOH versus EMF in the case of anhydrone and calomel electrode system. And now in the case of calomel electrode and hydrogen electrode or glass electrode system, what happens? So gradually there will be increase in EMF, and at the equivalence point there is a sudden increase. Once you find a sudden increase, take 4 to 5 readings and increase after sudden increase, then stop. Then plot the graph of volume of NaOH versus EMF. So this is the region of sudden increase in the EMF at the equivalence point. So locate the midpoint of this sudden increase region. Once you plot the graph, you have a linear portion where there is a sudden increase. So by locating or determining the linear portion, locate the midpoint of this steep rising curve. So volume of NaOH corresponding to this midpoint of steeply rising curve is the volume of NaOH consumed by whatever volume of HCl is taken. Right? So this is the nature of the graph for same HCl versus NaOH titration when you change anhydrone electrode to glass electrode or hydrogen electrode, keeping calomel as the same reference electrode. So this is where you have to understand. Do not just blindly draw the graph like this when you are explaining with anhydrone and calomel electrode system. This graph is applicable only for calomel electrode coupled with glass or hydrogen gas electrode for an acid-base titration. And if you are considering anhydrone electrode and calomel electrode system, the graph is the one which I had drawn earlier. So be careful when you are discussing about what electrode system you have chosen, and accordingly plot the graph. And again here, like locating the midpoint of steeply rising curve may have certain error in determining the exact volume of NaOH. So to overcome that, again we plot a graph of volume of NaOH versus delta E over delta V, as we have seen in the earlier case. This is called first differential graph. We can also plot delta square V over delta V square, the second derivative graph. Don't worry about that. This is sufficient. So when we plot the graph of volume of NaOH versus delta E over delta V, the graph is once again, we get a graph of this fashion, and volume corresponding to this peak is the volume of NaOH that is consumed by known volume of HCl taken in the titration vessel. So this is how it is possible to study acid-base titration by potentiometric method. So here, in any instrumental method of titrations, we determine the equivalence point from the graph. Remember that. Now let us consider redox titration. So we can also study or carry out redox titration by potentiometric method. So here let us consider the titration of ferrous ammonium sulfate against potassium dichromate. So potassium dichromate in acidic medium acts as oxidizing agent. So potassium dichromate oxidizes ferrous ions in ferrous ammonium sulfate because iron in ferrous ammonium sulfate is in +2 state, and dichromate ion in acidic medium acts as an oxidizing agent. It oxidizes Fe2 to Fe3 ion, and dichromate ion is reduced to Cr3+. Here chromium ion is in +6 state, it is reduced to +3 state, and Fe2 ion is oxidized to Fe3 state. So Fe2 is oxidized and dichromate ion is reduced. How it is reduced? Chromium in dichromate is in +6 state and it is now reduced to Cr3+. Okay, if it is sulfuric acid, you get Cr2SO4 thrice. So chromium will be +2 state. So it is a redox reaction. So when you are performing the titration of ferrous ammonium sulfate against dichromate, ferrous ammonium sulfate is taken in the beaker, potassium dichromate is taken in the burette, and dilute sulfuric acid is added to known volume of Fa is taken in the beaker, because dichromate acts as an oxidizing agent in acidic medium. So sulfuric acid is added to ferrous ammonium sulfate to maintain acidic medium. Then when we add a drop of potassium dichromate, what happens? Some of the Fe2 plus ions are converted to Fe3 plus ions. So after addition of a drop of potassium dichromate in the system, in the titration vessel, we have this type of ferrous and ferric ions. So you have iron now. After adding a drop of dichromate, this drop of dichromate oxidizes a few Fe2 ions to Fe3 ions. So along with Fe2 ions, now we have Fe3 ions. So you have both an oxidized and reduced species. So if you insert a platinum electrode into this solution containing Fe2 Fe3 ions, it acts as a redox electrode, whose potential depends upon the ratio of this. Okay, so it's a redox electrode. What's a redox electrode? A redox electrode is the one wherein a platinum electrode is dipped into a solution which contains same ion in two different oxidation states. If same ion is present in two different oxidation states in the solution, by dipping a platinum electrode into that electrode acts as a redox electrode. And in this case, platinum electrode is dipped into the solution containing Fe2, Fe3 ions. So what happens is that the electrode potential of this redox electrode depends upon ratio of concentrations of these two ions. Right. Okay. So during the titration of ferrous ammonium sulfate against dichromate, there is a change in concentration of Fe2 to Fe3 ion ratio. Okay, Fe2 ions are continuously converted to Fe3 ions. So Fe2 ion concentration goes on decreasing, whereas Fe3 ion concentration increases continuously. So the ratio of Fe3 to Fe2 or Fe2 to Fe3 ion changes, therefore EMF changes. Right. So now if you consider E naught of Fe3 plus to Fe2 plus is around it's more than I forgot this value. So this electrode, when connected with calomel electrode, okay, so calomel electrode acts as anode and this acts as cathode. I forgot E naught value of this, but this redox electrode, when connected to calomel, this acts as cathode. So if we can represent this cell as platinum this is cathode, or your first anode is written followed by cathode, right? So now when you have a platinum electrode dipped into a solution of Fe2 and Fe3 ions, and calomel electrode also dipped into the same solution. So this is the cell setup. E cell of this is given by the expression E naught of Fe3 plus or Fe2 plus plus 0.0591 by 1. How many electrons are involved? Only one electron is involved. This is the reaction. We consider always reduction reaction is considered as per IUPAC convention. So this is the reaction that is taking place at redox electrode. So we have this written as a minus A calomel. Right? So this is the expression. for EMF of this cell. The cell made up of redox electrode of Fe to Fe3 ions and calomel electrode. So when you look at this expression for EMF of this cell, which is used during the titration of FAS against dichromate, look, as more and more dichromate is added, more and more Fe2 ions are converted to Fe3 ions. So with the addition of dichromate, Fe3 ion concentration increases and Fe2 ion concentration decreases. Therefore, during the titration of FAS against dichromate, this ratio is increasing. So as this ratio increases, what happens to E cell? EMF also increases. EMF also increases. So as long as FAS is present in the solution, EMF gradually increases with the addition of dichromate. Once all the Fe2 ions are converted to Fe3 ions, next what happens? So as long as Fe2 ions are present, potassium dichromate added converts Fe2 ions to Fe3 ions, and dichromate ion itself gets converted to Cr3 plus ions. So during titration, along with Fe3 plus ions, Cr3 plus ions are also formed. So as long as Fe2 ions are present, dichromate added converts Fe2 to Fe3 ions and itself gets converted to Cr3 ions. Once all your Fe2 ions are oxidized, the next drop of dichromate ion added. The next drop of dichromate added does not undergo any reaction because Fe2 ions are already consumed. So next drop of, after equivalence point, the next drop of dichromate added does not undergo any change. Now Fe2, Fe3 ion redox system is changed to chromium 3, chromium 6 ion ratio. Now electrode potential after the equivalence point will be determined by this ratio because Cr3 plus ions are already present, and after equivalence point, if you add more and more dichromate ions, this remains constant because no Fe2 ions are present. Only dichromate ions are after equivalence point added. So with the addition of dichromate after equivalence point, this concentration goes on increasing. So this ratio changes, and because of this ratio, now EMF will be again changing. So as long as Fe2 ions are present, or as long as FAS is present in the solution, addition of dichromate results in the gradual increase in the EMF due to increase in this ratio. After the equivalence point, this ratio which was influencing the EMF of the cell will be now influenced by this ratio, and therefore at the equivalence point, after the equivalence point, what happens? There is a sudden increase in the EMF because of this ratio which is responsible for EMF. So after the equivalence point, and at the equivalence point, there is a sudden increase in the EMF because of change in this ratio to this ratio which influences EMF. So once we observe a sudden increase in EMF, we take 3 or 4 more EMF readings by adding 3 or 4 more liquids of dichromate. Then we stop. Then we plot the graph of volume of dichromate versus EMF. As usual, we find this type of graph. So identify steeply rising or linear portion of the curve, locate the midpoint, then volume of dichromate corresponding to this point, midpoint, is the volume of dichromate consumed by FAS. Either we can draw this graph, or we can also draw the first differential graph where we get a similar curve as we have discussed earlier, like this, or it could be like this also. So volume of dichromate corresponding to the peak would be the volume of dichromate consumed by known volume of FAS taken. So this is how we can determine, or we can carry out acid base as well as redox titrations by potentiometric method. Procedure is same. Take about 20 ml or 25 ml whatever volume of FAS you want, add about a test tube full of 2 normal dilute sulfuric acid, then place platinum electrode and calomel electrode, connect them to a potentiometer, add a drop of potassium dichromate, then you have Fe to Fe3 ion system, it acts as a redox electrode, you have a cell, then determine initial EMF, then determine EMF for every 0.1 ml of dichromate added, continue the titration till you get a sudden jump in EMF. After you find sudden increase in EMF, take 4 to 5 EMF readings, stop. Then plot the graph and calculate what volume of dichromate is required for complete oxidation of FAS. So let me stop here, and in the next session I will be discussing about precipitation titrations and complexometric titration. So please, if you have any comments to make, post them in the comments box. Thank you.